Hey, this video is in response to a student asking about a problem. So what I'm going to do in this video might somewhat take a long time. I hope that it's still efficient and clear though, and that you can learn a few different things from it. So what I'm going to do in this video is I'm going to spend the first part of the video doing some review of some basic things about driven LRC circuits. So driven LRC circuits. So I'm going to draw a picture of the circuit. I'm going to tell you what this driver is, and then I'm going to represent the driver with somewhat of a mathematical technique that looks like vectors, but it's actually Phasor. Forgive me for the spell. This thing corrects my spelling. I should change it. But that's supposed to be an O. It's a Phasor. So Phasor, Phasor. And when you drive an LRC circuit with an AC power supply, your circuit is going to have a response, and sort of the backbone of the response that physicists pay attention to is called the current. So we're just going to pay attention to the current because the current kind of tells us everything about the circuit. While I'm reviewing, we're going to talk about various reactances. Those are symbolized by X, capitals. There's an inductive reactance and there's a capacitive reactance. And in a sense, there's also a resistive reactance. But the resistive reactance is really simple. It's just the value of the resistance, R. In fact, all of the reactances have the SI unit, right, to describe them as just the SI unit of resistance, the ohm. Yeah, and then there is another sort of summarization of a LRC circuit's response to being driven. It's called the impedance, and that's given the capital Z as its symbol. We're also going to have to talk about phase angles, which is the origin of this sort of technique, or this little bit of technology called a phasor. Phasors help you keep track of relative phase angles very simply, graphically. So the phasor is just basically a representation of the phase angles. But I'm also going to have a reason to tell you about the relationship between, say, phasor diagrams and phasor angles, as well as graphs of the functions that the phasors represent. And then finally, I'm going to describe an example problem. I'll tell you what the problem is later. Yeah. Okay, so here we go. So some basics of driven LRC circuits. So the first thing we're going to do, let me look at my list. Let's think about what is an LRC circuit. So first of all, there's LR and C, and the particular combination that we care about for this particular discussion is to put an inductor in series with resistance in series with capacitance, like this. So here is the resistance and the capacitance, L, R, and C. L will take values in henries. Capacitance is farads. Resistors have values in ohms, right? Now, here is the LRC circuit, but we have a driven LRC circuit. So I'm going to represent that by this symbol, which tends to be a typical representation symbol, like this. And so I've got the linear, right? They're all lined up along one line. So this is not a parallel circuit, but a series circuit. And the rest of the circuit is just a wire, right? So this is a driven LRC circuit. So the driver, which is this thing right here, is an AC power supply. And the idea is it's going to supply a voltage. So I'm going to represent that with this electromotive force script E symbol, which varies in time. And we're going to be very specific about how this voltage varies in time. We'll say that there is an amplitude called E sub m, m for max, right? So that's the amplitude. This is some number of volts. And then multiplied by a sinusoidally varying function. So it's a function of time with an angular frequency called omega sub d. That's the driver frequency. And in fact, it's an angular frequency. And so later on, when I do this example problem, we're going to have some radians per second as how we're going to keep track of the meaning of the angular frequency, right? And then E sub m, this max or this amplitude of the voltage signal, is going to be some number of volts. So we have a sinusoidally varying voltage supply, right? You'll notice that this is, you can plug in different values of time. You could plug in t equals to 0, the value of the voltage is 0. And you can plug in t equals to 1 second later, and you stick it in there, and whatever the value of omega sub d is, right? Omega sub d times the second is radians per second times seconds. It just leaves over an angle. So what goes in the argument of sine functions and tangent functions and cosine functions is an angle, and we're going to stick with radians to describe angles. Okay, so there's a power supply. And if you draw a picture of the, right, you can draw this real quick. So this is E as a function of t, and it just varies like this as time goes into the future. And the idea is actually, yeah, it's got a function value for even negative times if you'd like. But yeah, sinusoidally varying, and it goes up as far as E sub m and down as far as negative E sub m, because there's no DC offset to this signal, right? Okay, so that's our picture. So in our list, though, I was going to describe the driver, but then I was going to describe a phasor diagram of the driver. So here, this right here, this function is our driver function. And I'm going to describe that what this looks like is the following thing. I can draw, or I can represent the value of the voltage as something of a clock hand, where I have an arrow that's called the phasor, and it's got an angle that references the horizontal axis. And this angle, I'm going to give the symbol, say, capital phi, right? That's the capital angle symbol phi, right? So here's an angle. And if you look at what this picture is showing you, let's see, I'm going to choose red. Okay, so what I'm going to do is I'm going to redraw this phasor in red like this, and I'm going to pick out where the projection of this arrow is on the vertical axis. And if this thing has a length of E sub m, then can you see that this thing right here is E sub m sine of this angle, right? All you got to do is draw your little triangle, right? So let me draw the triangle off to the side. So I've got a hypotenuse whose length is E sub m. I have a vertical side, right, which is here, and I have an angle, capital phi, right? And so that green side that I just drew is opposite to the angle phi. So opposite of our hypotenuse, right, is the length of the green, or opposite of our hypotenuse is the sine of the angle. So I hope you can see how this phasor, how this arrow So the arrow with its angle and its magnitude actually represents a particular value on the vertical axis, right? So that value right there is E of the angle phi, where the angle phi might be a function of time. For example, an interesting function of time is the angular frequency omega sub d times t, right? So so this is the idea. I'm re-representing this function. This is a function that has a graph that looks like a sine wave, right, in time, but that has a phasor diagram that looks like a little arrow that sweeps in the counterclockwise direction. It's sweeping like this, right? Where the angle 0 is the sideways, right? It's this is the angle 0. And so the angle phi increases counterclockwise, right? This is in fact matching how you might have learned how to read what's called the unit circle to keep track of angles. All right. So yeah, so this is how we're going to use the phasor, right? So all I've done is I've represented the driver's voltage as a function, as a graph, and a third way of representing the driver, right, the driver's voltage, is with this phasor. Okay, so let me continue. So I just told you about the driver. Now let me tell you about what's going to happen in terms of how the circuit is going to respond. So I've got this inductor, I've got a resistor, I've got a capacitor, and I've got this thing that's trying to force stuff to happen. In particular, what it's forcing is a current to run back and forth in the circuit. But the problem is because of how the capacitor, the resistor, and the inductor react, they all react in really funny time-dependent ways. So they have various reactances or reactions to being, to having this driver try to push and pull on electric charge or try to cause current to move around in the circuit. So here, I'm just going to tell you a basic fact. It turns out that the current that's going to flow in the circuit, right, is going to have some maximum value, that's the amplitude of the current, and then some sinusoidally varying angle, omega sub d times t. It's actually exactly the same as the driver's omega sub d. It's the same, but there is always, in general, the possibility that when the current is shaking back and forth, it lags or is sort of separate in time, in a sense, from the driver itself, right? So this right here is called the phase constant. And it turns out that this phase constant is pretty easy to define. You have to define a few things, though. You have to define what's called the inductive reactance. So the inductive reactance, the definition of this is you take the driver's frequency, angular frequency, and multiply by the inductance of the inductor in your circuit. You just multiply by the number of henries that inductor in your circuit is, right? There's also another reactance. It's called the capacitive reactance. It's how the capacitor is going to push back on the current, or in a sense, it has a reaction to the current trying to change, right? So this one, though, it's kind of strange. It's 1 divided by the driver frequency times the capacitance, right? And then there is a capacitive, a resistive reactance, but it's just the resistance. And it turns out, right, so if you're given, details about your circuit, you'll be given the inductance in your circuit, the capacitance in your circuit, the resistance in your circuit. You'll also be given the details about the driver. The driver has a driver frequency, omega sub d, right? So this phase constant actually is, you can compute it from these details. It's XL minus XC. So it's the difference between the inductive and capacitive reactances divided by R. Oh, excuse me. Actually, that's actually the tangent of the angle phi. So, yeah. So let me put a box around this. This is nice. This is important. This is important, and this is important here. And that's kind of, that's not an embellishment at all. Actually, this is also really important. These are all important review details. Okay. Cool. So, actually, check out what you know right now. You can almost completely write down how the circuit is going to have a current, because I just told you how to calculate this relative phase constant, this particular angle. It's an angle that's independent of time. It only depends on the inductance, the driver angular frequency, and the capacitance and the resistance, right? But there's another piece. It's the amplitude of the current. How big can the current ever get? And it turns out that there's a nice formula to be able to write that down as well. So the amplitude of the current, this I maximum value, it turns out it's equal to the driver's maximum voltage, right? This is the amplitude of the driver. So this is some number of volts divided by what's called the impedance, where the impedance is equal to R squared plus, take the reactance, inductive reactance, subtract off the capacitive reactance. You take this difference and you square it, and then you take the square root. Okay, so this thing right here has the SI unit also of ohms. It's somewhat of a resistance. So I've got a voltage divided by a resistance equals a current, right? But the way you read this, though, is that the amplitude of the oscillating or the AC current is equal to the amplitude of the driver or the AC voltage divided by the impedance of the LRC circuit at that driving frequency. So the impedance, right? Can you see that this impedance is actually a function of the driver frequencies, because the driver frequencies are in the capacitances, right? So this is an important detail. And now you can completely write down the current in the circuit, right? And as soon as you do this, in a sense, you kind of know everything about your circuit, or at least you have the backbone piece of information, and anything you might want to know about your LRC circuit probably has something to do with I of t, like what's going on at the inductor, right? What's going on at the inductor depends on I of t, right? What's going on in the resistor depends on I of t. The rate at which charge separation collects on the capacitor depends on I of t. So all the details of the circuit you might say that they start from this basic backbone knowledge of how the circuit responds, that is, how the circuit has a current because of the driver, right? Okay, cool. So, yeah, I've got a lot of things all done with this little basics review business, right? So I've got I of t. I've written it up here. I've told you how to get the amplitude of the current. I've told you that this you should just, there's reasons why the current is going to take this form. It's going to have an oscillation frequency that matches the driver frequency. So this omega d is the same as the driver's frequency. But when the current maxes out, you know, at the moment in time that the current maxes out, that's not necessarily the same as the moment in time that the voltage maxes out. They can have a phase difference that's represented by this phase constant right here. Okay, so now if the phase constant, whenever you solve for this angle, right, you're going to take the inverse tangent or the arctangent of this ratio of reactances, the difference between reactances divided by the resistance. So if phi is positive, then this is interesting. The current phasor lags behind the driver phasor. If the phase angle is smaller than 0, then the current phasor leads. In front of the driver. And if phi equals to 0, so how do you get phi equals to 0? Remember that the tangent, right? The tangent of an angle is really the ratio of the sine of the angle divided by the cosine of the angle. And so that means that the tangent of phi equals to 0 if phi equals to 0. That's what I'm trying to say. And phi equals to 0, or let me say it this way. If the angle was 0, then the tangent of the angle is also 0. And the way that the tangent of the angle can be 0 is if the reactances, inductive and capacitive reactances, actually have the same value, right? So somehow the value of 1 divided by the driver frequency times the capacitance in the circuit is equal to just the driver frequency times the inductance in the circuit, then you're going to get phase angle equal to 0, right? So this happens if XL equals to XC, right? This is also the condition of resonance. Yeah. So anyways, cool. All right, so I'm not sure why this thing won't let me. Oh, okay, so I can have another page. That's pretty dumb. All right, so okay, so now I've told you about a bunch of stuff. So, but now I've given you this list of ways to think about this phase angle. Okay, so here is an example. It's not yet the problem example that I was going to explore. So let's say, assume phi ends up being positive. So that means, yeah, so let's assume that phi is positive. You're going to get this, well, anyways, so yeah, let's assume that the phase angle's greater than 0. That means that the current phasor is going to be behind the driver phasor, right? So here is a point in time at which the driver phasor is here. So this right here is an angle, right? And that driver phasor has a length that's equal to the amplitude of that driver, right? So the current phasor, right, because the current is here, and here's that phase angle, and we're saying that if phi is positive, then the phasor that represents the current is going to be behind. So here is the current phasor, and it is behind, because remember that the way these things grow is they go counterclockwise. right? So this angle is omega sub d times t, and this angle is actually omega sub d times t minus phi, and the angle between the two phasors is phi, right? So this is what that phase angle shows us. And remember that the way you read the values, right? It says that so this is the voltage phasor, or the driver's phasor, and this right here, this projection onto the vertical axis, is the value of the time-dependent part, right? That's how it depends on time. So as the arrow sweeps over, right, it's going to sweep counterclockwise. Can you see that this projection is going to grow and then shrink down to 0, go down all the way to, the other side, and then come back up through 0 and just go back and forth. It oscillates like this. And this one, likewise, is going to do the same kind of thing. But its projection is here. So that's going to be where I of t is, right? Now, it's interesting, like, to look at the current in the circuit and the driver's voltage, but it's actually more interesting to look at all of the voltages, right? So there's the driver's voltage, there is the voltage across the resistor. Actually, let me, so since we're talking LRC, let's do L, R, and C. So these are all functions of time. And they can all be represented by phasors. And so here's my last sort of review point. So let me give the driver's voltage phasor a red arrow. Okay, so this is the driver's voltage. And we know that the current, let me do the current in black. So the resistor voltage is just whatever the current is times the resistance, right? That's a basic fact. And this carries over into the time dependence. So actually, let me... So the basic fact is that the voltage across the resistor in time is equal to the resistance, which is not time dependent, times the current, which is time dependent, right? So what I'm trying to say is that the voltage across the resistor is proportional to the current. Here is the current phasor, so we can just, this is how the proportionality is. So I'm going to draw the voltage across the resistor in black, and the voltage across the resistor is a phasor that's parallel to the current, right? Because they're in the same time. There's no phase difference. There's no phase angle between resistor voltage and current. So I'm just going to draw it here. So this right here is meant to be V sub R, right? Now here is another fact, right, that you can depend on. V sub L is always in front of V sub R by pi over 2. And V sub C is always, I'm going to underline always, in back of V sub R by pi over 2. Right, so these are the relative phases of the phasors that represent the voltage across the inductor and the voltage across the capacitor. So let's do the voltage across the inductor in blue. It's always in front by pi over 2. So if it's in front by pi over 2, remember pi over 2 is the same thing as 90 degrees. So the inductor in this case is going to have a phasor that looks like this. And then let me change the color to be purple, I guess. So a capacitor, it's always in back by 90 degrees. So the capacitor voltage phasor is back here. Okay. So this is the capacitor voltage phasor. This, oops. And this is the inductor voltage phasor. Once again, the angle phi is here. All right. So, the value of the voltage across the resistor as a function of time is the projection onto the vertical axis. The value of the inductor voltage as a function of time is the projection onto the vertical axis. And the value of the capacitor voltage as a function of time is the projection onto the vertical axis. And the idea is this is where you can see Kirchhoff's loop rule. Kirchhoff's rule says that whatever is gained at the driver, it's lost at the other elements. Right, so Kirchhoff's loop rule is actually in here. And everything is actually a function of time. Right, this is Kirchhoff's rule. And it's really just thinking about these projections. Right? Yep. Okay. So just a last comment. This one is a fine point, but I may as well bring it up. It actually confused me while I was trying to prepare this little lecture. So here's the fine point. So I just drew for you. Can you see that this V sub R is lagging behind the driver voltage by the phase angle phi? So what that means is that V sub R is going to be some amplitude. So I'm going to put V sub R max, right? So this is the amplitude times the sine of the driver frequency times the time minus the phase angle phi. All right. So what's interesting is these pi over 2s, these 90 degrees things. Let's think about V sub c. All right. So V sub c has to be 90 degrees, right? Talking about V sub c right now. Has to be 90 degrees out of phase with V sub r. And in fact, it's got to be behind, right? It lags. So the question is, I want to do this. I want to ask, so there's going to be some maximum capacitor voltage, right? That's the amplitude. But it's going to be 90 degrees. So 90 degrees different is either cosine, right? So if I just change sine to cosine, I'll get 90 degrees. But do I put plus or minus, right? So the capacitor voltage is going to either be a plus or minus with the cosine with the same argument inside as what the resistor voltage has for its sine. right? That's how I get this 90 degrees. You know, cosine and sine are 90 degrees different, right? So let me draw you a picture. So this is in time. And here is what, for example, the sine function looks like. Right? So that's the sine function. I'll just say it's sine of omega d times t. And I'll drop the phase angle just for a second. So let me draw a different function with a different color. I'm going to draw the cosine. So the way the cosine goes is it maxes out at t equals to 0, and then takes the value 0 when the sine function maxes out. So it's like, can you see this here, and then to there? So I just drew the cosine of omega d times t. And doesn't this look like doesn't the blue line look like it lags behind the black line? And then let me draw a third one, purple, right? This purple line is actually, oops, it's minus, right? The negative of the cosine. So the negative is just the opposite of the blue. So everywhere I look at blue, right? I'm going to draw the opposite. Okay, so I've got these three functions, right? So here's what I think is really important to say. And some of you may get this, some of you may not. So what does it mean to lag? Right? What it means is, for example, the following thing. Let's look at the black line. Let's pay attention to the black line. And let's pay attention to the fact that at this particular time, the black line has this value, right? But if I look at the blue line, doesn't it look like it's behind the black line? Actually, blue leads black by 90 degrees. And the reason is because, can you see that the black line is heading up through this value at this time, but actually blue already did that at the earlier time. Even though blue is being drawn to the left, being drawn to the left means that it happens earlier, because this is an earlier time than this. So actually, the blue line leads black. And the purple line, which is, can you see that it's drawn in front of the black line by 90 degrees? Lags behind black, right? It's in terms of time. Does stuff happen to one function before or after it happens to the other function, right? Up here, it's because the rotation sense is counterclockwise, right? You can definitely see that V sub L, the blue arrow, the blue phasor, is always in front of V sub R by 90 degrees. That's a right angle. And V sub C is always behind V sub R by 90 degrees, right? And in this particular case of phi being bigger than 0, because the inductive reactance is bigger than the capacitive reactance, that's the reason, we get the case where the resistor voltage is going to be behind the driver voltage. But if the capacitive reactance was actually bigger than the inductive reactance, then actually the V sub R, the black arrow, would be in front of the, it would be on the leading side of the driver voltage. All right, so that's basically all the background. I know that I forgot one thing. So can you see that the capacitor voltage lags? And I was originally asking, so are we going to put a plus or a minus sign on the capacitor voltage? Well, if the black line is the sine function right here, right? The black line is the sine function. The capacitor voltage needs to lag, so that means that it needs to be the purple line. So we need to choose the minus sign. So I'm going to go and choose minus. It's got to be this. And the voltage across the inductor gets the plus sign. So there's some amplitude of inductor voltage, cosine omega driver times time minus the same phase angle phi, right? So these are nice things to have. There's a detail that I meant to say earlier, but I'm going to say it just right now. Just a moment, looking at my notes. Okay. You need a way to be able to say what these max values are, right? Did I already tell you about V sub R? Let's see. Yeah. So I told you that I sub m is given this way. Here's I sub m. And so since I sub m is going to be here, then V sub Rm is going to be R times I sub m, right? Right here. So the amplitude of the resistor voltage is just R times the amplitude of the current, which I showed you how to get with the impedance. The amplitude of the capacitor voltage, though, is you take I sub m and you multiply by the capacitive reactance, and the amplitude of the inductor voltage is equal to I sub m times the inductive reactance. This is a nice set of details to have. Okay, so now that's all I needed to show you in order to show you a particular problem and how to solve it. Okay, so here's a problem. Got a driver. It's a sinusoidal driver. I have an inductor, resistor, capacitor in series, and that's all I have for my circuit, so I close the circuit with the wire. Here are some details. So driver details. The driver's got an amplitude of oscillation of 45 volts, so it's quite strong. And the driver frequency, the angular frequency, is 3,000 radians per second, right? So this is all the details about the driver, and the only other thing to do is to write down the functional form of the driver's time dependence, right? So this is how the driver works. Well, you just put in this 3,000 radians per second for that number there, right? With the amplitude 45 volts. The inductor has a value of, what was the inductance? Oh, sorry. Oh, it's embarrassing. I thought I had it organized. So here it is. Okay, so the inductance is 9.2 millihenries. The capacitance is 31.2 microfarad, right? So got milli on the one hand, millihenries, and microfarads in the capacitance, and the resistor is a nice easy 16 ohms, right? So here is all, oh, and there is, okay, yeah. So these are the details. So these are all the givens. So you know everything about LRC and the driver, right? Yeah, so here is the question. Rate at which driver supplies energy, right? So this is question A. What is the rate at which the driver supplies energy? Question B is what is the rate at which capacitor is gaining energy? Question C is what's the rate at which inductor gains energy? And question D is what's the rate at which resistor, right? Resistors, they cannot store energy electrically. What they do is they dissipate energy thermally. So they convert sort of organized, useful electrical energy into somewhat disorganized, useless thermal energy. So rate at which resistor dissipates heat, let's say, right? So these are the questions, and they are all asked at t equals to 0.442 milliseconds, right? This is at a particular time. You know that the driver is behaving this way in time. And with all of the stuff that we just went through, I gave you all of the machinery to determine how the circuit responds as a function of time, right? So here is the circuit's response as a function of time. From that, you can get the voltages across each of the devices as a function of time. Here they are, actually, right? Functions of time. So can you see that omega sub d, that was one of the pieces of information given. The phase angle phi, well, you have to figure that out. The phase angle is given here, right? Depends on the inductance, capacitance, the resistance, as well as the driver frequency. So all givens, right? Okay, and these are the voltages. So, but how do you calculate, right? So these are voltages, but how is this related to power? Right? Because that's what all of these questions are. They are questions about power, right? So, right, rate of energy. Rate of energy is the scientific statement of what's the meaning of power, right? So power. So, all right. So in order to do this, right? So remember, part A is rate at which the driver supplies energy. There's a formula. It's so the power of a power supply, it supplies power with the current times the voltage, right? So this is a power formula for how quickly a power supply like a battery can supply energy. And it's going to have units of watts, right? Joules per second, as an example. Right? Energy per time, joules per second. Okay, so this actually is what we're going to use, right? So in order to use this, right, so the power at a particular time is equal to the current at a particular time times the voltage at a particular time. So the time that we're interested in is this 0.442 milliseconds. So if you can come up with your function I of t, all you got to do is stick in 0.442 milliseconds. You'll get a value for I of t at that time, and you'll get a value for the driver's voltage at that same time. Yeah, and then, right, you just stick in 0.442 milliseconds in this equation right here. Pretty easy. Okay, so if you do this, right, you're going to have to write down I of t, right, which means that you need to find the phase angle phi, and you need to find the amplitude of the circuit's current response, right, I sub m, right? But I showed you how to do that up there, and so it turns out, and so I'm going to let you do it yourself, but here are some waypoints, see if you can get there. The current at 0.442 milliseconds is equal to 0.95 amps, right? So that's what the current is. Turns out it's about 0.95 amps. And the voltage as a function of time at 0.442 milliseconds is about, let's see, what did I wrote it somewhere. Maybe I didn't actually write it. I probably just, no, I wrote it 43.66. Right? And these two numbers lead you to saying that the power at 0.442 milliseconds is about equal to 41.3 watts. Okay. Now, here is something that's sort of difficult. Is this positive or negative? Right? We will say it's positive if the driver pushes on the current in the direction that the current is already going, right? So it's positive if it's trying to speed up the current that's already happening. But the power supplied by our power supply can be negative. It can be negative, for example, if you have a battery oriented this way, but the current flows backwards through it, right? That's how you recharge a battery. And recharging a battery is the same thing as that particular battery doing negative work, supplying negative power. So how do I know that it is positive? How do I know this? The answer is it's actually in the Phasor diagram. So if you end up doing everything, what you're going to find is the following thing. You're going to find that the phase angle phi is about 0.183 radians. And at the time t equal to 0.442 milliseconds, right, this is the special time, you're going to see that the phasor that represents the voltage is here, and the phasor that represents the current is here. And when you look at the projection, the current is on the positive side, and the driver is also on the positive side. And positive times positive equals positive. The power is positive because the current is in the same direction as the driver's push, right? So it's able to do positive work right now, supplying positive work per time. Okay. What's interesting is if you keep track of the inductor voltage is going to be on, it's 90 degrees in front of the current, but the capacitor voltage, we should expect the capacitor voltage to actually be negative when the inductor voltage is positive, right? Yeah, can you see that the inductor and the capacitor voltages will always have the opposite sign unless they're zero. When they're zero at the same time, which is interesting. Okay, so anyhow, here's a waypoint. I wonder if you can end up calculating that that's the power, right? And this is approximate. I wasn't keeping track of significant figures too carefully, but it's around 41 watts. All right, so part B. Part B is kind of difficult, actually. It's the, what is the power supplied to the capacitor, right? So really what this is asking is, what is the time rate of change of the energy stored in the capacitor, right? Well, the energy stored in the capacitor is 1/2 C voltage of capacitor squared. So this capacitance energy, right, is actually a function of time. It's 1/2. So capacitance is not a function of time, but the capacitor voltage is a function of time, and we have to square it. So if I want to know this, right, this is what the power is, the capacitor sort of rate of energy gain. I'd like you to see that the power for the capacitor is just d by dt of the energy stored in the capacitor. And the energy stored in the capacitor is in terms of the voltage across the capacitor, right? So if you take this time derivative, what's going to happen is you'll get C times the voltage of the capacitor as a function of time multiplied by the time derivative of the voltage across the capacitor as a function of time. So before you go, right, so this you can calculate, right? Because the voltage across the capacitor as a function of time is the amplitude multiplied, not by sine, but actually by cosine, right? It's going to be cosine of the driver frequency times the time minus the phi, like this. But do you remember this stuff where I was telling you that the capacitor lags behind the, so the capacitor, we need to put on this extra minus sign right here. So I'm going to put it on down here, right? So this is the capacitor's time-dependent voltage in this driven LRC circuit, right? And you know how to get everything. I've told you how to get the magnitude. You might have to rewind or look in the book or something. But it's got to do with the capacitive reactance and the amplitude of the current oscillations, remember? But anyways, should we expect this to be positive or negative? The answer, actually, you can see it in the Phasor diagram. If you just look at the capacitor. So remember that these things are going to be sweeping in time counterclockwise, which means that as time goes forward, actually this is the picture at the time in question. Can you see that at this time, this voltage is actually shrinking? It's shrinking. The voltage across the capacitor is shrinking. If V sub C has a magnitude that is shrinking, this is loss of energy, right? If the voltage is shrinking in time, at this moment in time, if the voltage is shrinking, then that means that the charge separation is shrinking. And if the charge separation is shrinking, the electric field is diminishing. And remember that the energy is proportional to the electric field squared, right? So yeah, it's a loss of energy. We expect this power of the capacitor at the time 442 milliseconds, we expect this actually to be smaller than 0. That is, 0 is bigger than this, right? We expect it to be negative. And you should make sure that it calculates to be negative. It's pretty cool. Like when you take the derivative is the reason it gives you the minus sign, actually, at this particular time. What about the inductor? So anyways, let me go on to tell you, just to give you the waypoint. So now the power of the capacitor is negative, let's see, sorry, it must be on another page there, 17 watts. It's about negative 17. Okay. All right. So the last thing I'm going to describe is, so this was part B. Actually, there's two other things. So part C. So the power of the inductor, right? It's the time derivative of the energy stored in the inductor, right? And the energy stored in the inductor, it's stored in the fact that you have been able to build up a current. So it's 1/2 Li squared, right? So you can imagine that taking d by dt of u sub L, it's going to give you Li di dt, right? So this is the power, or the rate of change of the energy in the inductor. Okay, so if you go, right, you can get all these things. These are all time-dependent things, right? So at the time 0.442 milliseconds, what you're going to find is the power, or the accumulation of energy at the inductor, is at about 44.1 watts. And then the power at the resistor. The power at the resistor is just I squared R, right? This is just a basic fact of resistance. It's something you learned probably in a much earlier chapter. So the power dissipated by the resistor as a function of time. So the resistance doesn't have a function of time, but the current does. So you have to square this, right? And yeah, this one's the easiest one to calculate. And it turns out when you calculate that, the resistance is dissipating energy at about 14.4 watts at the time t equals to 0.442 milliseconds. Okay, so yeah, these are the powers. Cool. So yep. I hope you found this interesting. It's a lot of analysis. I'm not sure how long this video took, but it's fairly long.